Hello everyone, good morning, good afternoon, good evening, depends on when you're watching this lecture. In this lecture, we're going to be talking about priority queues and heaps. When I was preparing for this lecture, one of the interesting things happened. I was preparing for, I was going to teach you about heaps first and then go to priority queues, because heaps is its own thing. But when I looked at the book, I found something interesting. Okay, the book talks about priority queues first, and then heaps. But when it talks about heaps, it implements them using a priority queue. So I'm like, okay. I guess they want me to do that. I was using the C++ book, so nonetheless, anyways, I'll go ahead and teach it the way they want. I guess it might be easier for you. Um, if you understand priority queue, and then I think it'll give you an entry, an understanding, easier understanding into heaps. So without further ado, let's get right into it. What is a priority queue? We all know what a queue is, right? Queues and stacks. We did study about them. We talked about them. It's straightforward, right? Um, but priority queue is a special type of queue. It's included in the standard template library. And what happens is each element in the queue has a priority associated with it. Um, this is what it looks like. So the element 9 has the highest priority. Uh, by you can insert elements in the queue, but what's gonna happen is inside the priority queue by default it's gonna put it in the descending order. So if you look at this, number 9 is up at the very top. So you can push elements in whatever order you want, but the top is always going to be the largest number followed by that. So it's always descending order by default. So if you haven't guessed, you'll include the queue library um, that actually has a priority queue in it as well, its implementation. And the way you declare a priority queue generic one is so you have the keyword priority underscore queue and then the type here and then the name of the queue. Okay, so let's say the type is generic, right? So you put in the type that you want in string, character, float, double, long, whatever you want. So here I'm creating a priority queue of integers called pq underscore integer. Right, and here I'm creating one for a string called pq underscore string. And this is a note, the same thing that I mentioned last slide is always remember. Um, you can store them whatever order you want, but in the background they're gonna go um, in descending order with the highest element up on the top, followed by the one after, so on and so forth. At the very bottom, it's the smallest number. You might be thinking, "Wow, can I change it?" Uh, Hold on to that thought. Maybe, maybe not, but that answer is coming. So stay tuned. And these methods, they should look very familiar, right? So you've got the push to add elements to queue, in this case priority queue. You got pop to remove elements from priority queue. Top, which is the element with the highest priority at the very top, right? Like I said, the way it stores them, it's in priority and the largest number is up at the top. So what do you think is going to happen? When you pop, you're going to get the element with the highest value. Size is simply just the number of elements. Empty, as the word suggests, it's going to tell you um, if the priority queue is empty or not. Now, with that in mind, let's jump into some examples. Get a few here. Um, I'm gonna walk you through the syntax. Include IO stream. Well, the examples in C++. For Java folks, let me know. But syntax is similar in Java and C++. It's close enough. In my case, I studied C++, I work on C Sharp, but majority of my career has been C++. I actually studied C++, but it was in C Sharp. But then recently, I started working on Java. and it was easy to pick up. A couple of weeks and I was good to go because the syntax is pretty similar. So in this example, I have a priority queue of integers, and I'm going to push three integers into it. 1, 20, and then 7. And then I have a while loop. While the queue is not empty, I output numbers at top, okay, whatever is at the top, and then I pop. Compilation terminal, what did I do? It main using namespace, main, did I miss a while loop, cout, endl? No. Doing a, should I do this? C++. What is the C++ compiler? Alright, because I've got C and C++, right? Let me go ahead and go to the C++ compiler. Program well, CPP. No, this one is okay. I want to run it. I gotta copy paste all of this again. But anyways, I'll walk you through it. Um, so the output of this method, right? So I pushed in 1, 20, and 7. And then while it's not empty, it's going to output the number at the top, remove it, and continue the loop. So when you run this, what's going to happen, you'll see the output is going to be number 20, right? Number 7, and then number 1. Whereas you pushed it in this order. Even, like, as I was trying to tell you, even though you pushed it in a different order, but it's still gonna do the largest one on top. This is the second example. Here, I've got a display priority queue method, um, and then I have a priority queue of integers. Then I push in 1, 20, and 7, and I say display the priority queue. And then I just do numbers at pop, so I just delete one item from there, and then I try to output again. What do you think is going to happen? Oh, man, what did I do? You include IO stream. Should have ran this before sharing it with you guys. Initially, it was, see, I pushed it the same example as last time. 1, 20, and 7, but when I output it was 27 and 1. And then when I did pop, then at that point it was 7 and 1. Right? This is the declaration right here. This is the type. So I hope you understand. Now you might be thinking, what's going on in the background? It is doing its own, it's actually doing a lot of work for you. It's a simple queue, but the way they've implemented it is they've got their own, they've got a logic in the background. So standard template library makes your life much easier, right? I hope you like it. Just an example. Sorry, I'm having to do this on the fly. So here I've got a priority queue of strings. C++, Python, Java. I pushed in 3 items, and then I'm seeing what's the size of the queue. This should be intuitive, right? The size of the queue is going to be 3. Um, so it's as simple as that. Next example. I am going to demonstrate how to use the method empty. So here, um, same thing, right? I've got a priority queue of strings, and I'm trying to use the method empty. Watch what happens. Is the queue empty? Yes. Pushing elements. Is the queue empty? No. So initially we just declared a priority queue of string called languages, and then if language is empty, we output yes. That happened because we didn't push anything. Well, then we said pushing elements, and we pushed 3 elements into it. And then we checked again. Well, this time it wasn't empty, right? No surprise there. That's just illustrating the use of size and um, an empty method. Um, the next thing I want to share with you is, let's see where it's at. Come on. Is mm, min priority queue. So what we were looking at was called the max priority queue, right? And as I mentioned earlier, is now you're thinking, can we change the order? Right? By default, it puts it in descending order. Can we put it in ascending order? Right? Um, yes, you can. And the way I'm going to show you an example, it's very similar, slight difference in syntax. So when you declare um, a priority queue, you need the greater this syntax in there. Okay, so let's talk about heap. Let's get into this. But before I get started, I did remember something. So I went back, looked at the book. The book implements the priority queue as a list. And then it talks about abstract data type in a specific manner. One thing I wanted to mention is, I did the priority queue using a queue, which is probably an easier way of teaching it. That was one of the that was one of the primary reasons. Um, but the point you should understand, the concept is, what is a priority queue in the sense that every element has got a priority associated with it, right? So it's ascending order or descending order. Now behind the scene, you have a list, you have a linked list, singly, doubly, or a queue. How there are different ways going about implementing a priority queue, but as long as you know the concept, you can use those data types. Now, the other thing to keep in mind is the runtimes. I want to tell you the runtime for each one of them. Let's say if you implement a linked list or a list or a vector or whatever, right? Um, or maybe this might be food for thought. Does the runtime change at all based on the type of data type that you use for storing the priority queue? Um, so, and then maybe I'll do a lecture just on abstract data type. We did talk about the templated function, generic function, which are useful, but I think templated class in and of itself is slightly more complicated. So I might want to dedicate a whole a lecture to it if I see the need for it. But right now, I think the way I taught priority queues is straightforward. Easier implementation, easier to understand. At least the concept that is. Okay, so heap. Heap is another data structure. It's a binary tree that satisfies these particular properties. So any given node, there are two types of heaps by the way. One is a max heap, and then the other one's the min heap. Max is The criteria for max is a given node is always greater than its child node, and the key of the root node is the largest. So if you take a parent, parent's always greater than its child. If you take that concept and you go each level up, right? So parent X is greater than its children, while the grandparent is greater than parent. Well, the great great grandparent is greater than the great grandparent. What will happen is you'll have a root that's the highest value. That's what a max heap is. Um, and then there's a min heap property. What that is a node is always smaller than the child node, and then the key of the root node is the smallest one, right? So now it's the opposite. A node, a parent is smaller than its children. Grandparent is smaller than the parent, and the great grandparent is gonna be smaller than all of his children. Uh, so what is it gonna look like? Um, so you've got a max heap. So this binary tree satisfies the max heap. Why does it do it? Because you've got 9 up at the very top. Well, let's take 5. 5 is greater than 1 and 3, right? Then you've got 4 that's greater than 2. But now looking at this picture, you've got 5 and 4's parent is 9. 9 is bigger than 5 and 4. And 5 and 4 are bigger than its children anyway. So 9 is going to be the largest one. I should have labeled this min. Now, in comparison to this, any node is smaller than its child. Right? Then the node's parent is gonna be smaller, and then if it adds something even above it, it's gonna be even smaller. So you keep going higher and higher, it's gonna keep getting smaller and smaller. In the max heap, the parent, well, the node up at the very top had the highest, or was the highest value, whereas here it's the opposite. This one has the lowest one. Now, heaps also can be created using different data structures. Um, this one, let's think of it as an array for now. So you've got this, think of it an array for now, then we'll get into trees. So you've got 3, 9, 2, 1, 4. And we get something like this at the end. So you've got 3, 9, 2, and then 1 and 4. Well, what's the difference here? That, this picture right here isn't really ordered in any particular way. Now, the way you go about making this into a heap is you start from the first index of a non-leaf node whose index is given by n divided by 2 minus 1. Right, so you get this node right here, the node 2. And then set current element to largest. The index of the left child is given by 2i plus 1, and the right child is 2i plus 2. If the left is greater than the current one, set the left child as the largest, right? If the right's greater than that element in the largest, then set right child index as the largest. You swap the largest with current element. That was all a mouthful of words right there. But what this is how to actually go about making a heap, making that binary tree a actual heap. Um, and you see, we are always worried about the largest one. Now, the way, I was toying around with this in my head. look at these steps. You really need to think through an example. We started off with this, so this wasn't a max heap because you had nine, which is the largest number in between, and then you get five sitting right there. So you start off with n divided by two minus one, so you end up with this number right here, right? And what we did in this case is we swapped. And what essentially we're doing is we're repeating these set of steps over and over again up until the root node um, ends up being the largest one. Call this method heapify. You set I as the largest, left child is equal to 2i plus 1, right is equal to 2i plus 2. If left child is greater than array at largest, set left index of the largest. If right's greater than array at largest, set right child index of the largest one. And then you swap array I and array largest. Because you're trying to get the largest one. But I think you really have to play with examples out yourself. I was thinking of drawing out examples, but I tried, but it still doesn't get the point across. But look at this algorithm. This is the algorithm for actually, I call it heapify. You can call it whatever you want, creation of a heap, or the process by which you're going to make your array a heap. But because even if you've got these indexed, um, it's fine. And for creation of the max heap, you loop from the first index of non-leaf node down to 0. You call heapify. And then for the min heap, both left child and the right child must be larger than the parent of all nodes. Because min heap's kind of like the opposite, right? The child's got to be larger than the parent. Okay, so let's talk a little bit about inserting elements into a heap if I didn't have heapify and heap completely confused you. This might do the trick. No, I'm just kidding. I think insertion and deletion is fairly straightforward. So for max heap, how do you insert an element? So this is the algorithm. If there's no node, straightforward, there's no tree, nothing, you create a new node. Else, if a node is already present, insert the new node at the end. Last node from left to right. So what you're doing is just inserting another element, going from left to right. So say a node's going to be on the right hand side, depending on if you get a left one, right? And then once you've kind of shoved this element over there, then you call heapify the array. And then what was heapify? If you remember, this is the algorithm, right? So you keep swapping, you keep running through this until you get the largest one on the top. So you insert an element in that spot, and then calling heapify is going to make this into a max heap. How do I know? I just know. No, this is the algorithm. This is what it's supposed to do. Now another way that you might be thinking is, it didn't come to my mind, but I know it might come into your mind. How about you rearrange the tree in such a manner, or you create rearrange the tree in such a manner and then add a node. So you've got these references all over the place, but that I think is a little bit more complicated. This one is more straightforward of a method. Well, how about you want to create a max heap, right? So you have that heapify method. Max heap takes an array and a size. Loop from the first index of the non-leaf node down to 0, and then you call heap. Right. So heapify does one portion of the work, but looping from the first index of non-leaf node all the way down to 0. You keep doing this over and over and over again. At the end, you've got a heap. And for the min, both left and the right child must be larger, right? So min is slightly different. Uh, so okay, so by now you should know what a heap is and the difference between max and min heap. Okay, so now let's talk about deletion of an element. If the node to be deleted is a leaf node, who cares? Nothing's gonna change. Just remove the node and you're done. Otherwise, you swap the node to be deleted with the last leaf node. And this is from left to right, right for the max heap. And then you remove node to be deleted. And then you heapify the array. You swap it, delete it, and then you heapify it. It's gonna happen. You get this element 3 that you want to delete. You swap them, then you get rid of this 3 because it's got no children, and then you heapify the whole array so you end up with the appropriate order. Um, right, in this case, I don't know if a whole lot's going to change, but the point being is you call heapify because this way you actually get a proper heap. And once again, the algorithm for heapify is something that I've shared with you. So what I want to do right now is walk through an example in code. This one's in C++, but like I said before, the Java syntax is similar. Um, in this, I've got a swap method. A swap is important because remember we said in the algorithm that you need to swap the elements. So I've created a swap method, and then I've got a heapify, the one that I was talking about, insert, delete, and then printing of the array. The main driver, the driver method, the main method, it inserts 3, 4, 9, 5, 2 into this so-called heap tree, and then prints it, and then it deletes the node 4 and then prints it again. But you're wondering where's the magic happening? Because I'm just calling insert. Well, it's happening in insert. When you insert it, you heapify the whole tree. Now, one thing that I think the slide didn't mention is, well, we'll get to it. So let's look at the mistake here first. Um, the insert, and then you got to do something similar for delete too. So you insert an element into the heap. If there's no node, no problem. You create a new node, and you're done. It's as simple as that. It's a brand new tree. Otherwise, if a node's already present, insert the new node at the end. You go from left to right, and then you heapify the array. But then you've got to heapify. You've got to run some sort of a loop. And that's what you can see in the example. So you insert it. You look at the size of it. Oh, so the insert method takes in the vector, your actual data structure as a reference because you want to change the contents of it because you're going to call heapify, and then you take in a new number that you want to add. So int size equal to ht dot size, heap dot size. You need the size because if there's no elements there, then you just push back and you're done. Otherwise, you push back, but then you loop for calling heapify. So now look at this. The start of the loop, size divided by 2 minus 1, okay, and then you keep decrementing I until I is greater than or equal to 0, right? So this is, and you're going to do something similar for delete as well, so you might as well remember this loop. You're starting from size I 2 divided minus 1, and you keep decrementing, um, you know, until it's greater than or equal to 1. And then you call heapify with your data structure and I. Now what does heapify do? Heapify is heapify takes in an array, size, and then an I. And then you set I as the largest, and left child equal to 2I plus 1, right is equal to 2I plus 2. If the left child is greater than the array at largest, then you set the left child as the largest. If the right child is greater than the array at largest, then you set the right child as the largest, and then you swap a at I and a and array at largest. But obviously, you gotta keep doing this up until well, this is heapify, right? So you know, sorry, I was getting confused with delete. So you don't loop. You loop and insert and delete, and you keep decrementing until you've gone through all the nodes. But here, so I've got the heap and the I, left child, right child, 2I plus 1, 2I plus 2, and you set I as the largest. Alright, and then I'm checking the size here. If the left child is less than size, and then right child is less than size, and right, heap at largest is greater than HT at largest, left child at the largest. This condition is true, right? There's a bitwise operator, so both of these conditions have to be true. Then you set largest as equal to L. If right child is less than size and heap at right is greater than heap at largest, both these conditions are true, then you're going to set the largest to R. Now, if I is not equal to I, then you swap I at largest and then you heapify, right? So it's not a loop right here. You call it heapify again and again. Alright. I've got insert, I've got heapify, delete is up next. So what do you do in delete? Check the size, and then you have your I equal to 0, I less than size, I plus plus 1. If num, right, the number that you've received is equal to heap at I, then you break, and then you swap h at I and then h at size minus 1, and then you pop back. Right, you just delete that element. Well, you've deleted the element, so keep in mind when we're doing it. I think for this one, the picture is going to help you a little bit. We identified 3 to be deleted, and we swapped 3 and 5, and then we just pop back this 3, and then you heapify. That's how you get things back in order. You pop back right here, and then you see the same loop for insert, it's here as well. So you keep looping and keep heapifying until you get a proper heap. And then print should be straightforward. I mean, you start off at 0, go till size, increment I, and then you output heap at I. 95342 and then 9532. So I think this was quite a bit for you guys to take in. Like I said, it's the other thing. We didn't talk. Like I said, we didn't talk about the template class or abstract data type. I'm gonna save that for later. But for now, ponder upon, think about the priority queue and heap, and I'll have a cool homework assignment in a day or two for you guys. All right, take care.